Hello everyone, this is I'm Prathamesh Jadhav. I'm presenting paper ID 216 with the name Smart Wearable for the Visually Impaired. The other authors of this paper are Anamed Dhepe, Namita Chandrasekhar, Ashwini Kulkarni, and Shakaina Ezekiel. This will be the outline of the PPT. Objective: India has the highest number of blind people in the world. There are around 39 million people affected. 25 million people are blind, and some of them are moderately or severe have visual impairment. The leading causes of blindness are cataract and refractive error or some kind of diseases. Our proposed system is a smart wearable device which can be used by a blind person to understand his surrounding, to read a particular text, to call his friend, to video call his friend to get help from him at if in for navigation or at some point of emergency. And we also provide an obstacle or object detection functionality. Our model helps mild to moderate impairment people with reading a particular text or to make them understand their surroundings using image captioning. Our system can also be used by dyslexics or an illiterate person to read a particular text from a pamphlet, newspaper, or any other kind of document which they want to read. Literature survey, some of the paper tried solving this problem. One of them was smart glasses for visually disabled person. They use an ultrasonic sensor with a camera uh, to detect the familiar faces. This was done by OpenCV. Ultrasonic sensor helped them detect an object in close proximity. The next paper, which tried doing this with was design and implementation voice assisted smart glasses using Google Vision API. So they used a YOLO V3 pre-trained model to detect objects. These detector objects were told to the user in his ear using an audio output. The third paper uh, was trained on public signs. They trained their model to understand certain public sign or street signs so that they can give an audio output to the blind user. The fourth model was the fourth model used an uh, depth camera. The depth camera was used to generate an AR rendering or a depth AR depth rendering, which was used to understand a particular object or a particular path for an for the blind users, so they were navigated using that. There are various existing systems. Some of them are mentioned here: Seeing AI, Nurcam AI, and New Vision. These these systems have their own functionality, but we have our own proposed system which try to accumulate all the main functionality needed by the blind user for a good price point. As you can see here, the functionalities we provide in our system are obstacle detection, which we do by using an ultrasonic sensor, image captioning. We have an our own built AI model which helps blind user describe the particular surrounding around him. Then we have OCR to read the documents or and to detect the words written or the text written in the document to the blind user, and we have video assistant in our system also. This is the methodology. There are four compartments. The first and the leftmost is obstacle detection. This is done by ultrasonic sensor. So if there is an obstacle or an object in tri close proximity, a text file or trigger text file is created by the ultrasonic sensor, which is then converted to a audio output the text to speech functionality to the blind user's ear to make him understand there is a particular obstacle in front of him. Then there is capacitive touch sensor also. There are three capacitive touch sensor with everyone with different functionalities so that the blind user can press a particular button if he wants certain functionality. One of them is image captioning. So if a user triggers a button or clicks a button, then the image is captured from the camera. This image is processed by Raspberry Pi, and the Raspberry Pi hits an API which is present in our backend cloud, AWS cloud. So the Raspberry Pi has Python scripts which send the image to our backend cloud, which has our AI model, which is image captioning model. This image captioning model takes the image and describes the image for us. So it is all done without any human involvement. We have trained our model to generate a good description of a particular image, which is then which the description is usually English text, which is sent back to the Raspberry Pi, which is present in the glasses. The Raspberry Pi then converts the text into audio, which is sent to the user's ear. Then, so if user press the button, he can understand what is happening around his surrounding using image caption. The other button uh, is OCR. So if user clicks an OCR button, the same process happens, but here there's an OCR model in our cloud. So the image gets sent by the Raspberry Pi to the cloud. The cloud converts extracts the text out of the image. So then the text is then sent again back to Raspberry Pi, which converts the text to speech and dictates the particular text to the user. The third button is for video calling. The After clicking the third button, the blind user can call his friend for navigation, either in navigation or in case of emergency, if he wants his talk to his friend, or he wants help from his friend to navigate through a particular situation. This is our image captioning model which we built. It is an AI model which has encoder and decoder architecture, and it takes an image as an output and generates a English sentence as an image as an input and generates an English sentence as an output. So in encoder, the encoder takes the input as images. It converts the images into features, or the context features we call it. So in what happens is, a Resonate 101 is a pre-trained CNN model. It's a big and a good big model which converts the images into some kind of features which the model understands, which the AI model understands. So these images are converted into features. The features are generally some some kind of obstacle features, or different features for different objects. So these images are converted into features which are inputted to decoder. Now decoder takes this feature and converts the feature to English sentence. So this is done by an attention block present here, and an LSTM cell. LSTM is a long-term short-term memory cell, which is an RNN, which is used to generate a recurring output. In here, the recurring output is the English text. So the attention layer helps to get the best weights. Weights are generally used in AI models to optimize the output. So the attention block helps to get the best weights and get us the better description of an image. So this model is trained on our data set of images and their description. So after training it for quite long, we can get a good description for a particular image. As you can see, these are the results. As you can see in the left, is a girl drinking water from a bottle. Now, if here the photo was clicked by uh, through our system, the click photo, and we got the output like following: a woman in black shirt is holding a bottle. So this output was heard in the ear by the user. So this kind of description can be generated by image captioning, which I showed the block diagram a slide before. Now this is the OCR output. So as you can see here, the document can be read by our model, and the output will can be dictated into the blind user ear. This is the video calling feature. Uh, if he wants the blind user wants help of his friend, he can video call his friend and help ask him for navigation. As you can see, the wearable device look like the following. There are three capacitive touch sensor for three functionalities: OCR, image captioning, and video calling. And there's an ultrasonic sensor, green ultrasonic sensor here, which runs real time to uh, to make a blind user be cautious of his surrounding. These are some references. Thank you. Again, my paper ID is 216.